Next speaker is Alex ZS6EME. Alex knows his way in moonbounds for quite some time now. The problem is, he keeps changing call signs. After his time in Peru, he just started getting used to his Swiss call sign, HP9DRI, and now he appears to be in South Africa. Maybe he's just trying to get DXCC in a special way. Anyway, Alex is a talented designer of electronics, and this time he's going to tell us all about his new development, the UADC4. Good luck.
Thank you. Thank you, Jan. First of all, guys, sorry I catch a cold yesterday with the aircon on the bus. My voice is not the best. Okay, I think so this one works like that. Let's go and speak about the UADC4. Is my last development together with Live Osbrink and some other clever designers. We will speak about the introduction is happening now, about zero IF receiver technology is old, why we have DDC radios, software defined, many ready-to-use solutions, and we will speak about the audio cards and the UADC4 design per se, and at the end I will speak about a little bit performance. Okay, zero IF receivers are used in the history of the radio from the beginning practically. But zero IF receiver has a big problem, and everything related with mixers creates always unwanted signals. Phase noise in the local oscillator also create problems with reciprocal mixing when strong signals are in our passband. And yes, well, all the direct digital converter technology and enthusiasts say to us, yeah, everything related with mixers is old technology, and today we are with DDC receivers, full digital. This is really old technology. But I'm not in agree. I'm not in agree, and for just we need to review what DDC conversion. For those ones who don't understand, do you have a pen? A pen. For this will not draw a big one. Direct conversion receivers, direct digital conversion receivers, what they are doing is they are converting the radio frequency signals. Yeah, this one. If we have the ADC here, they sampling directly on the antenna. Sampling directly on the antenna, that means here is no any analog device, no local oscillator. Everything is happening in the analog to digital converter. And direct digital conversion is extremely clever, it's extremely fast, but has some problems when we are talking about wake signal communications. ADC technology, when it's accumulated directly with sampling on the antenna, have many advantages compared with traditional mixers. And these advantages we can list. For example, we sampling on the antenna, what is a big advantage. That means everything entering the digital domain immediately. We can use NCOs, numerical computer oscillators, quite are nothing else than oscillators built by software inside the conversion board, the ADC board. Normally they use FPGAs. Yesterday we have the option to watch one of these units when we walk in the second floor in Astron. We see many Altera FPGAs. Means radio astronomers, they love digital, direct digital conversion, and they can sample big amount of bandwidth in milliseconds. The phase noise is not any problem with the reciprocal mixing. That means that doesn't create really a problem with phantom signals. And well, that is the promise, that this is cool and let's go use it. Let's go try to use it, DDC, like many enthusiasts. But from the perspective of moonbounds, we have several problems here. First of all, sampling big amount of bandwidth, it's really necessary. Okay, if you go for pulsars, yes, but I'm talking about specific, in this moment, if you go for pulsars, yes, but in moon bounds, you need really this big amount of bandwidth. That we are confronted with this idea that more is better. That means more bandwidth is better, more megahertz in the clock speed, in my computer is better, bigger my house, I feel more successful, or whatsoever. What about the dynamic range? That means more is better, always, we know perfectly. And depending where your antenna is located, dynamic range play a big role for everybody. It means not everybody have the chance to have locations like you, Barry. Sorry. Or like HWinIQ in Switzerland, or like many other ones who install antennas in areas where man-made noise is not a problem. We are installing antennas in densely populated areas where dynamic range play a big role. And what can the market deliver today in this way? And what about the implementation cost? DDC technology exists, and exists especially for frequencies in an affordable money for ham radio enthusiasts up to around 80 megahertz. But everything going up to after 80 megahertz turn exponential in the cost. And assume all this DDC stuff need to include a traditional transverter in the front. The promise of sampling on the antenna just vanished because you introduce all the traditional behaviors of mixers, local oscillators, and phase noise. Okay, the DDC technology over 100 megahertz today lack of enough dynamic range. They have an excess of bandwidth for amateur radio applications. For more than 20 years, and this is the point where we talk about these PC audio cards as a digital converters. For more than 20 years, we use audio cards because it was nothing else available in our budget range, with extremely great success. But today, these audio cards cannot add one single bit of any more performance to our systems. And we didn't have better zero EF receivers, that means mixers sampling directly and down to basement, because the limiting factor was always the audio card. And this is exactly what I will explain. Audio card, even if they are sampling at 24 bits, they limit their characteristics to just 20 kilohertz. No more. That means 20 kilohertz is probably the maximum a human being can hear. Why manufacturers would extend extraordinary performance over 20 kilohertz? In that way, our brain and our ears are an extraordinary limiting factor for the performance of an audio card. And these audio cards, even if they sampling at 192 kilohertz or 384 kilohertz, they preserve an extraordinary performance in just the first 20 kilohertz. And then the performance decrease in many aspects. The limit is there. Is just 20 kilohertz of good performance, and the rest is marketing. But we don't have other options. And I am an enthusiast of software-defined radios, and successfully, many years ago, I built the famous IQ Plus, that is in use for many stations. And well, simply, I tried to reach a better performance for the radios I produce. And I was confronted always that the limiting factor to have better performance in dynamic range, better rejection in harmonics, increasing the crosstalk between channels was always the audio card. I have a big box at home with more than 30 different audio cards. I spent a fortune testing audio cards from $20 to $1,500. And even the most expensive cards, probably one of the most beautiful cars I use, the MU1616 PCI Express from Creatives, was in the range of $800, was produced 2 years and was retired of the market because the card was too good. And today you can find the card for almost the same price in the second market. Very hard, but the price still. That means it was very difficult. That confronted me when I decided to build my own ADZ, specific for software-defined radio. I was confronted that I cannot build chips. I need to use chips already on the market. And after analyze 4 different brands and do 4 different prototypes, I select the ADC from AKM, the AK5574. Quite the characteristics are explained there. Can go up to 127 dynamic range in 4-to-1 configuration. But I select that chip because I test where this limit of 20 kilohertz, how it works in the different brands. And the other brands, after 24, 25, 26 kilohertz of sampling, the noise roll off very, very, very quickly in the corners. That means it was not used really for us. And all those who has already using sampling, audio cards for making ADC conversion, when you increase your bandwidth, you see the response is not really flat. And that creates many, many problems with wake signal. Then I try to analyze, why, if this chip is so good, other implementations didn't exploit better. And this is, for example, a copy of the buffer stage proposed by the manufacturer, what is a disaster as a buffer. Is exactly what you don't want. In digital conversion, you need to fit differential the channels. But you have an analog input. That means you need to convert one analog signal, single signal, in an analog signal, but differential. And the problem here is, if somebody of you knows and works for sure with op-amps, this is not a real differential single input differential output amplifier. The main problem is here. When the jumpers are installed, this op-amp is looking the signal through this op-amp. That means we have an active device coming here when this input signal just comes straight. And I found this one in every single audio card. And what is the problem here? Look the resistors. My source resistor is 4.7 kilo ohms. The feedback resistor is 4.7 kilo ohms. They are in a ratio of 1-to-1. Okay? That means it's preserving the amplitude. But this is an active device, and this active device introduces delays in the time domain, and that creates serious problems. And these are not symmetrical. I did hundreds of hours in LT-SPI simulations, and I always have between 20 to 120 millivolts amplitude differential between these two. Something completely unacceptable when you want to convert an analog signal in a digital signal. That means I was forced to completely design my own buffer for the ADC. This is not really good one, but this is recommended by the manufacturer. And another problem is, if you see power supplies, oh sorry, I will back. If you see power supplies swings plus minus 50 volts, when the maximum amplitude is 2.81 volts. That means, looks like the manufacturer released this information and allowed the other people who adopt the system to create some kind of control volume input. All audio cards have digital controls in the input, and they are noisy because they work with digital resistors, and they are very, very noisy. Even a potentiometer here is extremely noisy. And the last but not least, if you see the values are extremely high. And in the op-amp domain, when the higher the resistors are working in levels up to more than 1 kilo ohm, you introduce thermal noise. And this could be acceptable for sound card and music applications when you have a lot of harmonics running one over the other one, but not in software-defined radio. That means I designed my own input buffer. The details about the input buffer and the characteristics are on the proceeds. I will skip that part. The other important part in the design was how we can select the clock. Audio cards, even the good ones, they use horrible, extremely cheap clocks to make the sampling. And we decided to use this one. It's an extraordinary, it's an overkiller. I'm pretty sure we can use even another one, but the price was very, very tentative. Looks at 10 kilohertz, the phase noise, minus 160 CDBC per hertz. This is an incredible performance. And in ADC sampling, it's very, very important. Most of the audio cards not even has minus 132 dBc per hertz on the local clocks. Then starts the nightmare to design the PCBs. And I found that if design electronic will be just drop components, will be very easy. Nothing affects the performance of this ADC converter more than a PCB. And for example, that is a copy of one of the first iterations we did. It was this chart, doesn't work because it has a lot of magnetic loops capturing a lot of noise. This unit compared with the last unit we tested, it was 15 dBs more noisy. And just because the PCB, moving capacitors 3-4 millimeters within the PCB, making traces 1 millimeter wider or smaller, it have a terrible influence in the way the system is converted in a magnetic noise pickup machine. Well, the other part is we was forced to go in 4 layers because the analog domain and the digital domain in terms of ground need to be extremely separate, but they need to be together just in one single point. And I never work in 4 layers. That means I need to learn even CAD design and many things. I will go just quickly. We have, for example, the power layer, and later on all these layers are in a sandwich just 4 millimeters wide. You have the ground 2 layer and the signal 2 layer. We did in totally around 6 different prototypes, one better than the other one, and until we reach the performance we expect. Now I will detail here. How many minutes I have? 15, that's okay. And in the proceedings, it's an extensive document where it's long detail. Well, the UDC performance, first of all, as usual in all my electronic designs, I try to involve Live, Sugar My 5B as said, because he's a hardware tester with no commercial interest with nobody. That means even if he's your best friend, and you produce a crappy electronics, he will say in public, sorry, you produce crap. And we know, everybody we know Live, he speaks friendly, open, sharply, and sometimes he tells us uncomfortable truths. When you are a designer, that was the story of the IQ Plus. Live, before the IQ Plus went into the market, he said, no Alex, that's not good, again and again and again, many times. Well, Live was, he showed me a lot of the secrets of the ADC conversion. It was a 4-year process, learning, reading books. I never did ADC conversion by myself. That means do the electronics, demand, learning all this, the theory, and then apply. When this was well built, we was in Proto 3. We reached excellent flat noise response up to 192 kilohertz. I will say perfect response noise up to 96, and very good up to 192. The chip can sample up to 768, but I will never use this chip because over 192, the noise just roll in a horrible way. The harmonics was tested using the ensemble soft rock, no? And only to give an idea, this 85 dB attenuation in harmonics, when you test the ensemble soft rock with the top audio card you have today for affordable price, what is the DMX6 Fire from Teratech, The DMX fired with the soft rock give you minus 45 dBs harmonic attenuation. The UADC4 running with exactly the same radio give you minus 85. That is 40 dBs better response in attenuation for harmonics. And all this stuff is documented in the videos live published in his YouTube channel when he did the test. The crosstalk between channels is in the range of minus 110 dB. Audiophiles proclaim and they declare minus 120, 110 dBs is a trade-off. I can improve this one up to 140, but then my harmonic response is lower. That means I need to make a balance. 110 isolation between analog channels is extremely enough for a software-defined radio application. And then we test with different mixers in front of the UADC. For example, the combo, the WSE converters from live, they reach an incredible performance. The detailed numbers are on your proceeds, but just to give you an idea, the WC converters together with the Delta 44 give a noise floor of minus 145 dBc. The UADC4 integrated with the WSE converters give minus 162.8. This is a tremendous reduced of the noise floor. And I don't need to explain you what happened when our noise floor is lower or higher. I think so all will appreciate better lower noise floors. In the IQ Plus modified, the improve is in the range of 11 dBs. When we spoke about dynamic range, that demonstrated me that my design, based in the mixer 5517 for linear, was underutilization. And it was in underutilization because the sound cards I used at the time the IQ Plus was designed was too noisy. The noise floor was too high. Having the UADC with lower noise forced me to modify the IQ Plus. And the dynamic range, I reached the maximum dynamic range the chip can deliver, quite is 121 dBs. Now I will go straight to one important point. If you tell me, okay, cool, if I took my software-defined radio, call you your mixer, your IQ Plus, your WC, and you install your audio card, do you will feel a difference in the performance? And I will say no. And the answer is very simple. All the software-defined radios based in ZeroEF technology, like SoftRock, IQ Plus, WSC, or individual implementations with traditional mixers and oscillators, have an excess of gain in the analog part. And the IQ Plus, to work properly, need to be modified, just reducing the gain of the output amplifier by 20 dBs. That means it's replacing 3 or 4 resistors in the audio stage of the IQ Plus allowed you to move the saturation point from minus 26 dBm to minus 9. That is, in theory, the IQ Plus will tolerate 17 dBm more stronger signals. But due the reciprocal mixing for the local oscillator, I cannot claim totally these 17 dBs, I can claim 11 dBs. Better performance can be reached if you replace the local oscillator for a better local oscillator, existing many other options. And what is really important is out of the box, without doing so much modifications, Live published an extensive comparison of all the audio cards available on the market, tested with software-defined radios. And the UADC4, without doing nothing, just dropping and changing for removing the sound card and changing for the audio for the UADC4, it was automatically positioned in the table in position 1. Now, that is in terms of changing your sound card for a better UADC. But here, my point and my main contribution is The UADC4 is here. It will enter in production soon in a limited number of units. It will be available, and it will be valuable for everybody who is doing software-defined radio. I speak a lot about digital. The best proof of that is, as I say, digital. Dominic Fassler just ran away of the room. Well, okay, it's his problem. But this is nothing about JT. When we spoke about digital, even microwaves, even if you are only a CW guy, just sit and demonstrate to us you are using a lot of SDR applications to sampling and identify your noise. Imagine all these applications running in a performance with 15, 20 dB lower noise floor. And last but not least, I mentioned, and it's very well detailed in the proceedings, you can read there, all the software, you have many software-defined radios, especially for HF. They don't go more higher than 100 megahertz. And if you find something in 144 megahertz, good luck. But they sampling at 16 bits, at 18 bits. And in the document is explaining the difference when you change the bit sampling, how your dynamic range go up and down. That means this is a new window of opportunity, because what we need now is we need better mixers. And it's possible to design and to have better mixers. I'm working in the next generation of the IQ Plus. It will be the IQ Plus Pro. It will reach the market in maybe 4 or 5 years. But better mixers can exploit the extraordinary performance of the UADC4. That means it's here. We don't need sound cards anymore. But sound cards are for music, not for software-defined radios. That's my presentation, and thank you very much.
Thank you very much. I think there will be some questions. Yeah.
Alex, during the development and design process, the so-called magnetic pickup, what you showed,
Yes.
Could you put it in the simulation, or is it doing by try and error?
No, it's a try and error. You know how Live did? It's a video in YouTube. Here you can see one of these videos. Live used a magnetic coil, 220 volts, 10 amperes.
To search for
He
them.
blew up 10 times the fuses in the house. He was in Skype with me and in TeamViewer, and then, freeze. Waiting 10 minutes, sorry, I blew up the fuses. And he was using this magnetic coil to identify the problematics. And we put many other audio cards and we test.
Okay, that was my question. Yeah.
No.
Cannot simulate.
You can't simulate in an EMC professional software. I don't have access to that software.
More questions? Well, I guess they all want lunch.
Yes.
Well, thank you very much. It's very interesting. Thank you.
Thank you.
Here, a small book about the Netherlands.
Okay. Thank you very much.
Okay.
Thank you.